So the next talk will be from Jun Ouyang, who has several affiliations, but from Xiaodong University and Hunter College, and will be telling us about BZT, looks like.
Yes, thank you. First of all, I would like to thank the organizers to give me this opportunity to talk about my recent work in domain engineering. I have a review paper with my advisor, Dr. Roybert. He's not here today, by the way. Based on the method of domain engineering, we applied to the material system of barium zirconium titanate. It's a collaborative work, as you can see, with several groups, and also including my new position I just took last month in the Qilu University of Technology, which aims to be the one of the top engineering schools in China. So first of all, I would like to give you a bit background. So the ferroelectric films, as we know, the intuitive application is memory. But recent days, people are more focused on the use it as an energy material for energy transformation and for energy storage. I think Professor Len Martin gave a very good presentation yesterday about using it as a heat recycling device, which is really good. I enjoyed it. And what I want to propose here is everything can come from a structure property relationship as a material scientist. So a very typical one is the how to engineering the usually square-shaped ferroelectric hysteresis into a slim one, which is good for capacitive energy storage. So that's one good example. Then I want to maybe using a few slides to talk about domain engineering, which basically I talked about it last conference 2 years ago in Carnegie Institute, but I would like to just refresh the memory. So there are two types of important domains. One is the polytwins of the same phase. So very good example in the literature is PZT. People try to engineer it to get a large piezoelectric, pyroelectric, or electrocaloric effects. And also bismuth ferrite, the 109 and the 71 degree domains. Another type of domain, maybe not that commonly seen, but it's very important, is the so-called heterophase domains. We have the example of bismuth ferrite, a T-like phase and R-like phase. I think a lot of people know here. But also applied to the system I'm going to talk about here, the zirconium-doped barium titanate. I'll show you it's very good for energy storage applications. And that's the kind of picture you can have. You have domains here, and from engineering point of view, you want to harvest the most out of the domain movement. So if you have a mobile structure, if you apply a field, there will be a very large or very substantial amount of extrinsic contributions from the domain wall movement. And I'll give you a snapshot of the previous finding, which we published 2 years ago in Nature Communication. Then I'll show you some of the most recent results. So basically, it's a tetragonal and a rhombohedral stacked structure, and a very slim hysteresis, and a very endurable to electric cycling. And then the new data, mostly structural data, and our new understanding based on the structural data coming from the X-ray pole figure analysis. So what is the phase boundary between tetragonal and rhombohedral phase? It turns out to be a surprise to us. And the HRTM and Hardif STM shows us the polarization distribution in atomic scale. And also we have some nonlinear optics results, which I myself is not an expert, but I try to show you the big picture. And then I'll end with a summary of our understanding on the role of phase boundary. So as we know, ferroelectrics, if you think about all these properties derived from this intrinsic ferroelectric polarization, we can call it an energy material. You can use it in energy harvesting, energy conversion, energy conditioning or buffering, or energy storage. So I don't need to say too many words about it. Then films is good for integrated devices. And when you grow a ferroelectric film, or more generally a perovskite film, you need to consider all these effects like interface effects, the strain effects, and the lattice defects. Most importantly, how to deal with the oxygen vacancies. And with that, you may think about different ways of engineering. First of all, you have to control the defect. in the film. Otherwise, you get a very leaky film. You have to think about the interface as a gate to control the charge transport. And in epitaxial film, you can use a strain to create all kinds of nanostructures. And lastly, the grains in polycrystalline film also plays a very important role. The grains and grain boundaries, how to engineer them and give you the best available property. So I'm going to focus on the epitaxial strain effect in today's presentation. So we know this hysteresis very much, right? This is ferroelectric, as you can see it. It's good for memory application because you have a very, very large relevant polarization, and it's also good for piezoelectric transducing applications because your piezo constants basically scales with remnant polarization. And there's another type of ferroelectric hysteresis. It's very slim, very small remnant polarization, and intuitively it's good for charge storage or electrical capacitive energy storage. So how to engineer them? So if you think about ferroelectric film as a homogeneous system, it has a lot of microstructure, inhomogeneities, which I would like to call. You have interfaces with the bottom and top electrodes. You have grains and grain boundaries, which separates polarized region. And you also have domains and phase boundaries. All these inhomogeneities have different ways of engineering, which I basically summarized in a recent book published last year. So now this is my favorite slides in every single of my presentation. I would like to spend a few minutes about the concept of elastic domains. So we know that as you have a phase transformation from pyroelectric to ferroelectric, you reduce your symmetry. So you're going to have orientation variants. Here I'm using a cubic to tetragonal transformation. So you have twins. So that's well known in crystals and in bulk materials. But if you put it on the substrate, the physics changed a little bit. Let's say if you deposit high above the Curie temperature, it's a high temperature deposition. So basically, let's say you can relax most, if not all, of the misfit strain with the substrate. Then you cool it down. Now it goes to the point of phase transformation. You have a choice of either goes to the black domain or the white domains. But either way, you're going to create a lot of lattice mismatch because now your lattice changes a lot. So single domain is not stable based on thermodynamics because you have a large, long-range stress field. Mixture of domain is more stable. So in this case, comes with the concept of elastic domains. So you're going to have a self-strain, and you're going to have multivariant product phase, which basically it's satisfied in almost every single solid, if not all, solid phase transformation. But the constraint here is really the key. Why we call it elastic domain for the A and C domain in tetragonal, because it is really the elastic constraint that gives you the driving force for the formation of the polytwins. So put in single words, homogenization to eliminate long-range stress field under epitaxy, leading to the self-assembled polydomain structure, leading to the formation of the self-assembled polydomain structure. I use another slide, maybe it's more clear. The following slide shows the analogy between elastic domain and the electric domain and the magnetic domain. So we know the formation of electric or magnetic domain because of depolarization or demagnetization effect. So you forming this kind of 180-degree domain can eliminate the long-range stress field and reduce it into a stray field. Similarly, elastic domain has the same similar physics. So you're eliminating the long-range stress field, and by forming the domain variants, you're basically reducing that into a micro stress field. And all this formula will be the same. The domain period will be a square root of the feature length. So everything is in perfect analogy. But difference is, this elastic domain I think is more common. It's a much broader concept, not only in ferroelectric, but also in semiconductor, in ferromagnetic films. You all can see the fingerprint of elastic domains. So this is the review article I just mentioned. I think that's a very good summary of the progress in elastic domains and applications. And also, I would like to mention another type of domain. Let me just finish this two type of domain first. So again, if you summarize, you have a high symmetry phase. It goes down to low temperature, lower symmetry case. You can have you can form the stable phase in the bark, like B and B prime. They're just orientation variants. You can also have a choice of a metal stable phase, which does not exist at all in bark. But under the elastic constraint, this phase can be stabilized. It's just like the T-like phase in bismuth ferrite, right? So if you have large enough energy barrier, you can form the kind of two different phases, parent phase, product phase, or two different product phase. If your energy barrier is not that high, you can form polytwins. So all these two types of domain is to serve the purpose of minimize the long-range stress field or minimize the elastic misfit energy. But there's another type of domain which we just maybe don't have enough time to mention. It's supposed to be in the poster last night, but my advisor, due to his health condition, he did not come today. But this type of domain, I want use maybe 30 seconds to talk about it. There can be domains that appear in highly stressed films, not serving the purpose of eliminate the stress field, but serving the purpose of reducing the stress or reducing the misfit energy. If I show you the free energy chart, you can understand what I mean here. So you have two material, free energy or elastic energy as a function of the misfit. They have different modulus, you can see from their curvature. So first type of domain forming near the 0 point, small strengths. So they're forming the polydomain to eliminate the elastic stress. But if you go further away from the 0 point, you can see you can draw another common tangent. So this common tangent connecting two sets of domain which still have stress, but it's better than you have single domain variants. So this type of domain is possible to be formed in highly stressed films. But that's not the focus of today's talk. So three types of domain, but we're going to focus on the second type, the heterophase domains. And like I mentioned, it can be in a lot of different materials, ferroelectric and non-ferroelectric. You can use the concept of elastic domain to study this, the related phenomena in these film systems. So I guess all of you familiar with A and C domains. I just want to showing one slide, try to recap what we learned from there. Of course, depending on the misfit, you can either have 100% C domain or mixture of C and A or purely A domain under tensile strain. And because the polarization vector is rotated by 90 degrees, that's why we call it 90-degree elastic domains. And in TEM, you can see them. They're forming a kind of three-dimensional network in the film. And one of my paper about more than 10 years ago is about how to change the symmetry, breaking in the symmetry of the domains to reduce the number of variants. Therefore, you can have a much more mobile domain structure rather than the films with all the three variants, which kind of interlocking each other, preventing each set of A domains to move. So that's a work of more than 10 years ago. And today I want to talk about basically how to using the polydomain structure to store more capacitive energy in a ferroelectric capacitor. So we know the best idea dielectric is a linear one. Basically, you don't have any loss. When you charge and discharge, the efficiency is 100%. But the problem with this kind of materials, they have very low dielectric constant. So you cannot store too much energy in a single capacitor. Ferroelectric instead, you can store a bit more, but problem is it has a hysteresis. So if you charge it from 0, you go to saturation, you go back. There's still remnant polarization, which kind of pin down all the charges in the capacitor. You cannot release all the energy you stored in the capacitor initially. So people think about all different ways to engineer ferroelectrics. So they talk about decreasing the initial dielectric constant so you can delay the saturation, then you can store more energy because the energy density scales with the square of the field and only linearly dependent on dielectric constant. So the maximum field you can apply is more important. Well, that's right. And obviously, if you can improve that field, you can store more energy. But the key here, I think, is really how to reduce the remnant polarization, right? To make the stable remnant polarization as small as possible. In this case, you're not only increasing the energy stored and discharged, you're also increasing the energy efficiency. So that's the key we want to achieve here. In order to reduce that, we want to have a stable polydomain structure that gives you almost a zero remnant polarization. So that's the motivation of the work. So to do that, we thought about the second order or hierarchical domains. So we know that formation of domain is a mechanism of reducing long-range stress. So if you grow only single variant, you have huge stress. I use a color to represent the intensity of the stress. So single variant, huge stress. If you grow first order domains, you eliminate most, but not all the stress. You still have some residual stress, in this case, in the film. And if you grow the film thicker, you can form more higher order or fishbone-like domains to eliminate this kind of residue stress. But at the same time, you're creating more interfaces. So it's a trade-off between interface energy and the bulk elastic energy. Now, you think about this kind of domains. So now you go from microdomain to nanodomain. So in each of the nanodomain, your polarization has a unique orientation comparing with its labels. So it's really not good for memory application because the polarization is going to be really hard to pull, right? The apparent polarization, you try to align all the dipole on the same direction, but when you have all this, so many nanoscale domains, it's really difficult to pull, right? But that's good for storage of electric charge. So if you think about it further, if you have a single variant of domain, you have a remnant polarization, you saturate. Then when you go back, the single domain, let's say if the single domain is stable, you still have some charges bonded to the surface of the capacitor. You cannot discharge them completely. But if you begin with a zero apparent polarization, let's say if you have a head to tail polydomain structure which is stable at zero field, then you go pull them, it's going to be really difficult to pull because this is stable. Then after you're using a really large field to pull them into about the same direction, now you basically charge the capacitor with a lot of electric charges. Then you want to discharge, you're reducing the field, then the polydomain structure go back to its original stable structure, which is the head-to-tail polydomain with a zero apparent polarization. You can discharge almost all the charges you previously stored in the capacitor. So that structure is really good in terms of charge-discharge energy storage. So if we draw that schematically, you can think now I have two sets of domain, the green system and the blue system. So inside of them, they have different orientation variants. They rotated into the screen by some degree. So the first order domain is between the green and the blue. So basically, they are elastic and electric domains. They are about micron and submicron kind of scale. If you talk about domains in a thick film, micrometer thick film, this domain is going to be micron scale or submicron scale. But if you look at these nanodomains inside each of the microdomains, these domains, basically the change from one variant to the other variant only costs a tiny amount of energy. So we are basically breaking down the energy barrier between the two different color domains, breaking from a huge barrier into small steps. In this case, these domains can align with the field step by step. So that's the kind of ideal scenario we want to achieve in this material. So we have this domain structure figured out, and can we do it experimentally? So we choose the rhombohedral system. Kind of too fast. We choose the rhombohedral system. We know rhombohedral system, you have basically four different variants. If you consider 180 degree, then you have 8 different domains. Now this domain, you can combine them into two sets of 1, 1, 1, right? Now their domain boundary will be 1, 0, 0. So this kind of domain is purely geometric. You can construct it without any experiments. But can we do it experimentally? So we know that barium titanium is very good dielectric, right? It comes with really high dielectric constant. That's why we pick this system. But the pure barium titanium is very stable tetragonal at room temperature. It's really hard to tune them into a rhombohedral by simply using strength. So we think about by using the power of doping. So zirconium is a bit larger B-side ion than the titanium. So if you dope with zirconium, you're going to increase the volume of the unit cell, and it will change from tetragonal into rhombohedral. So we have that phase diagram from the literature, but we know when you grow it in film, everything will change a little bit, right? Basically, when we talk about the epitaxial growth of these perovskites, we usually grow it in a compressive strain substrate. In this case, tetragonal phase will be stabilized. So we want to grow pure rhombohedral, but we know because of the symmetry of the substrate, it's almost unavoidably to get some mixture of phases. So the question for us is how to control them. So we can control, obviously, by selecting substrate, right, with ideal amount of misfit. We can also control it by changing the film thickness. The thicker you grow, the smaller the misfit strand will become. So with that, we know that the BZT composition we choose is 20% because it's deep into the rhombohedral. And we are hoping that we can get rhombohedral dominant structure when we grow really thick film to eliminate the effect of strain. And this composition, we know from the X-ray analysis of the box ceramic, it has a lattice parameter about 4.1 angstrom. And we pick the substrate in this range. Lanthanum aluminide oxide and strontium titanate. It's a really good range. And we started actually 3 substrates, LAO, STO, and also the LSAT right here. So they all have different misfit. 5 more minutes. Okay. So we know that the, maybe I skip this, just directly go to this. If you grow the film really thin, so you can see the heterophase domain will be more stable if you grow really thick, really thin here. If you grow really thick, you can basically forming a polytwin structure between the rhombohedral variants. So we grow the film by using the sparring technique. And then this is the SEM picture of the film, very dense and thick film, about 2 micrometer thick. And the previous results was published 2 years ago, like I said. Very high energy storage density and efficiency, as well as very small losses and the temperature stability. It's all due to the ultra-adaptiveness of this kind of nanodomains. And we really see these nanodomains from TEM. This is a microdomain across the whole film thickness. And when we zoom in, we found the coexistence of 2 different phases, the R phase and the T phase. And we look at here, actually, sorry about the bad time management, but I want to say one more thing about it. We try to figure out the phase boundary between the 2 different phases. This is rhombohedral, this is tetragonal. From one of my previous theoretical work, we are thinking the boundary should be 112. Basically, it's 111 plus 001, you get 112. So it's very, very natural. But it turns out this angle tells us this phase boundary is not a 112. Then that's why we did some X-ray pole figure analysis. It shows us very interesting patterns. So this is a 002 pole figure, and the 111 and 101. We did all these 3. And also for different type of substrate, it shows exactly the same pattern. Then based on this specific angle, like you have two sets of 4-fold symmetry near the 48 and 49 degree in this 002 pole figure, and there's another set of 4-fold symmetry near the 70 degree, which seems to be right in between the 2 sets of 4-fold scattering spots. Then finally we figured out this is not 112, but instead is 122. This interface between the tetragonal and rhombohedral phase. And with that, we're trying to figure out why. Because theoretically it should be 112, but that is based on the isotropic elasticity. That tells us this tetragonal rhombohedral-like phase, they have hugely anisotropic elasticity. So these 2 phases, when they meet together, there's going to be a lot of lattice distortion as well as the charge compensation between across the phase boundary. So that phase boundary, we think, will play a very important role in the performance of this material. And we did the STM analysis, which shows us this polarization, the red, the light blue, and the blue and the greenish blue. It shows us that these 3 different regions has a different average polarization. This is A domain on average, this C domain on average, and this is rhombohedral on average. So the polarization are really locally variable. They're not forming the kind of domain that we know in the textbook or in previous literature. They're really kind of like in random states at the local scale, but statistically they show kind of symmetry there. So that brings us to think, what is the physics behind that? So we know if you have a homogeneous bulk, BZT is a rhombohedral, it shows this kind of ordered domain structure. But if you have a tetragonal stabilized, a stress stabilized tetragonal phase there, and the mix with each other at the local scale, you have phase boundary in between them. Basically, you're creating a random electric field, a random noise, and this noise can be really high when the mixture of them happened at a very small scale. And Professor Chen's group in Penn State, they did a very nice phase field simulation, and it tells us with this inhomogeneous mixture of phases and the random noise, we can really delay the saturation of the polarization and makes it extended. And I'm going to skip all this here and just show you the result of these pump probe results. It shows us by doing the faster Fourier transformation of this pump probe signal, it tells us these two phases, one is rhombohedral, one is tetragonal, they differ very much in their elastic property. You can see from their featured or characteristic frequency from this acoustic wave experiment. So our hypothesis of highly anisotropic elasticity, I think, is proven by this pump probe experiment, which we did in Hunter College. So with that, I'd like to thank you for your attention. And if you happen to be interested in my book, which published with Elsevier last summer, I'll be happy to discuss it with you. Thank you.
Questions for June?
Very nice. So I had a quick question. So the lattice mismatch is so big between all the substrates that you picked, right, for the LEO, LSAT, and STO. Does it have any impact on the density of the domains? Are they all relaxed? I mean, can you really tune the density of these twin boundaries in that lattice mismatch range?
Very good question. Yes. The lattice mismatch, as you said, is really big. It's like more than 3 or 4 or even 5 or 6%. So we grow the film really thick. It's like more like a 2 micrometer, but we did find that the film is still stressed. It's not totally relieved because of the huge amount of the initial strain. And we did the analysis of these the film grow on different substrates. So we invented a way to tell how the domain ratios will be by looking at the pole figure, because we now know which spots coming from tetragonal phase, which spots coming from rhombohedral phase. We can compare the ratio of the intensity. It does have a huge dependence on the strain.
Do you know the mechanism for the residual strain in the thick films? I mean, they're huge.
No, we haven't have a clear idea yet. But one of the hypotheses is because of the way that these domains, the tangle with each other at nanoscale, there's interface strains as well. The phase boundary acts kind of like a tree to hold all the leaves together. So the average strain is still there, but locally they are kind of compensated. So.
Other questions? Maybe I can ask a quick question then.
Yeah.
So in these highly strained films, do you see a lot of dislocations? And do they affect the properties?
Yes. These films, we call it epitaxy, but because of the flow thick, we also did a local TEM analysis. They're kind of distorted region. We suspect it's near the phase boundary. They are like even not well crystallized region. So of course, dislocation will be no-brainer. They're even like hugely stressed region. They comes out with a polycrystalline kind of diffraction pattern. So we would like to call it maybe pseudo-epitaxial because it's so thick. And they're so, the scale of the phase mixture is so small. So obviously there are a lot of defects there, maybe more than dislocation.
Any final questions? If not, let's thank June again.